Welcome to the problem-solving session for Chapter 29. Let's begin with the first question. Here we are given 4 cases in which we are asked to determine the direction first of the magnetic force in each arrangement. Secondly, given the value of Q as a magnitude of 5 microcoulombs, V as a magnitude of 1 megameters per second, and B as 2 Tesla, determine the actual value of the magnetic force in each case. Well, what we want to do here is we want to consider, in the case of the direction, the product, if you recall, F, magnetic force, as Q times V cross B. B being the magnetic field, V being the direction of the velocity, and Q, of course, the charge itself. So in the first case, we see that V, this is a positive charge, is along the positive I hat direction. B, the direction of the magnetic field, is along the minus K hat direction. And if we use our little I hat cross J hat cross K hat wheel, we see that I hat cross K hat is minus J hat, but we have a negative already, so this becomes positive J hat direction. So this is the direction of FB. In the next case, we have a negative charge, and it's moving along the negative I hat direction. But because Q is negative, negative times the negative I hat becomes a positive I hat. B is upward, so we're going to cross to J hat, and that gives us I hat cross J hat, the direction positive K hat for FB. Here we have a positive Q along the negative I hat direction. B is along the positive I hat direction, but I hat cross I hat is 0. So there is no magnetic force in this case. Here we can see the positive charge moves along the positive J hat direction, and we're going to cross to B. Now B has components because it's lined up 45 degrees to the horizontal. And so B will have a component perpendicular to the velocity, which is the positive I hat direction, and a component that's parallel to the velocity, which is in the positive I hat J hat direction. Only this component, however, is the one that we are going to consider because magnitude-wise, you'll see that there will be a reduction in the magnetic force due to the fact that the B itself is not entirely along the I hat direction. However, for purposes of determining the direction, J hat cross I hat gives us J hat cross I hat a minus K hat direction for the magnetic force. Well, once we have the direction, now we can proceed to obtain the value of FB in each case. Of course, keeping in mind that in case C, FB will be equal to 0. So, in the first case, FB is equal to 5 microcoulombs, that's our Q, times 1 megameters per second. And keep in mind here, micro is 10 to the minus 6, mega is 10 to the plus 6. So these two actually give us 10 to the 0, which is 1, times T, times the sine of 90 degrees. Of course, we know that because I hat's perpendicular to minus K hat. And lastly, the direction that we've already determined, which is the positive j hat direction. Since we aren't writing this as a vector, we need the direction to be there. 5 times 1 times 10 to the 0 is 5, times 2 is 10, times 1, sine of 90, we get 10 newtons in the positive j hat direction. In the case of B, we're still going to have the same magnitude of 10 newtons because the sine is still 90 degrees, except that we decided the direction based on the cyclical permutation of I hat, j hat, and k hat was positive k hat. In C, there was no magnetic force, and in the case of D, we expected to have a magnetic force that would be smaller because there was an angle of 45 degrees we had to contend with. We were no longer dealing with the sine of 90 degrees. And of course, the direction we said was minus k hat. So here we end up with minus 7.07 newtons. And of course, it's the minus k hat direction. I just happened to put the minus in front of that. Next question. Here we're told that there's a positive charge, 3.2 e to the minus 19 coulomb, that moves with a velocity 2I hat plus 3j hat minus k hat in a region where there's both a magnetic and an electric field. The magnetic field is 2I hat plus 4j hat plus k hat. The electric field is 4I hat minus j hat minus 2k hat. In the first part, we're told to calculate, and notice they're using the term Lorentz force. Well, the Lorentz force is simply the sum of the electric and the magnetic force, that is known as Lorentz, on the charge Q. And then we're asked to determine the angle that the Lorentz force makes with the positive x-axis. Well, there is a video animation which we're not going to get to see because although I may be able to click on it, I'm not so sure if it's going to work. Well, let's go ahead and work this out numerically. Let's start with part A, and how about if we get the electric force? The electric force being given by Q times E from chapter 23. Well, we have 3.2 e to the minus 19 times 4I hat minus j hat minus 2k hat. Okay, we're going to proceed with the straight multiplication, and my approach here will be to take 3.2 times 4, 3.2 times -1, 3.2 times -2, and to carry the e to the minus 19 at the end. So we start with 12.8 I hat minus 3.2 j hat minus 6.4 k hat, and we put a little parentheses there, e to the minus 19 with the unit of newton. Next, we want the magnetic force. Here, we have to do a little bit more work because we have Q times V, and that multiplies vectorially, vector product, with B. So, let's start out. Q is 3.2 e to the minus 19. We'll multiply that by V, 2I hat plus 3j hat minus k hat, and that cross 2I hat plus 4j hat, if I'm copying my numbers correctly, plus k hat. Well, we'll start with the first part. And again, I'll use the same approach. 3.2 times 2, 3.2 times 3, 3.2 times -1. And then I'll take that vector and cross it with b. All right? 3.2 times 2, we get 6.4 I hat plus 9.6 j hat minus 3.2 k hat. And of course, this will be e to the minus 19. And we're going to cross that with 2i hat plus 4j hat plus k hat. And here, let's go ahead and just draw off to the side so that we can keep reminding ourselves I hat cross j hat cross k hat. And we'll use the FOIL method of multiplication for each of the terms. So we start with 6.4 I hat cross 2i hat. Well, of course, that gives us 0, so we don't even have to write that. 6.4 I hat cross 4j hat. That gives us 25.6, the positive k hat. 6.4 I hat cross k hat. Well, that gives us minus 6.4 j hat. Next term, 9.6 j hat cross 2i hat gives us minus 19.2 k hat. 9.6 j hat cross 4j hat, well, that's just 0. 9.6 j hat cross k hat gives us plus 9.6 I hat. Next, negative 3.2 k hat cross 2i hat gives us minus 6.4 j hat. Minus 3.2 k hat cross 4j hat gives us plus 12.8 I hat. And of course, all of this, oh, lastly, 3.2 k hat cross k hat is just 0. So this is e to the minus 19. This way we don't have to keep carrying the powers of 10 throughout. Well, now let's go ahead and combine all of our I hats with all of our j hats and all of our k hats. So we've got 12 I hat plus 9.6 I hat gives us 22.4 I hat. Negative 6.4 j hat minus negative 6.4 j hat gives us minus 12.8 j hat. And then we have 25.6 k hat minus 19.2 k hat gives us a plus 6.4 k hat. And again, e to the minus 19. Now, all we've obtained is FB. So in order to get the Lorentz force, we have to take this and add it to FE. And recall that FE was 12.8 I hat minus 3.2 j hat minus 6.4 k hat, and that was also e to the minus 19 newtons. Sum these terms up and we get a total of 35.2 I hat minus 16 j hat. Let's make sure that that's correct. And the k hats cancel, so this e to the minus 19 newtons gives us the Lorentz, or the net force, on the charge Q. Now, the next part, okay, the unit here is the newton. The next part says, determine the angle that this force makes along the x-axis. Well, let's see. we have an x component which is positive in the positive x direction, a y component which is in the negative direction, so negative y. What quadrant might that be in? Yes, the fourth quadrant. So here we can either write the angle that we get as a negative angle, which we understand it's an angle measured clockwise from positive x, or we can take the negative angle and add it to 360. Let's just go ahead and leave it as a negative angle for the time being. The inverse tangent of 16, of course negative, and that'll be because it's in the fourth quadrant, divided by 35.2 gives us an angle minus 24.4 degrees. And of course, as we said, we can take this and add it to 360, and we give the angle counterclockwise from the positive x-axis. Next question. Here, we are given an arrangement of 3 segments of a wire in the shape of a right triangle. The right triangle makes an angle 55 degrees along the line BA. And you can see that the length of that line is 2 meters. Now, because we know the length of this line, let's go ahead and work up a way to express the length of this line, because when we use the expression FB, we will use I, the current in the wire, times L cross B. And so just alone for the magnitude, we need to know what the length of the segment AB is, with the length of the segment CB and the length of the segment BA. Now the length of the segment BA we already know is 2 meters. Well, if you look over here, the tangent of 55 is equal to AC over AB. Well, AB is 2, which means the length AC is equal to 2 times, so this length of this side is 2 times tangent of 55. If we look at this length right here, because it's the hypotenuse of the triangle, we know that the cosine of 55 is equal to AB over CB. Now, we want CB, therefore, CB is equal to AB divided by the cosine of 55. And AB is 2, and we're going to divide that by the cosine of 55. So let's go ahead and proceed, and we can use the right-hand rule to get the direction. But first, let's go ahead and get the magnitude for each segment. And we'll start with the segment AC. Let's start with this segment right here. So AC, we have an FB magnitude, which is equal to I, 4.7 amps, times L. Our L is 2 times the tangent of 55, times B. B is 1.8 Tesla, times 1. 1 because the angle between AC, the length of the wire, the direction of the current, let's say that, which is the positive j hat direction, so this is in the positive j hat direction, and the direction of the magnetic field is the positive I hat direction. Well, these make a 90-degree angle, so we have the sine of 90, which is equal to 1. All right, let's go ahead and obtain the actual vector as the product of 4.7 times 2 times the sine of 55 times 1.8 times 1. That gives us 24.2 newtons. The direction here is going to be j hat for I cross I hat for B, which gives us a minus k hat direction. Now, let's go ahead and work up CB. CB, the magnitude here is FB here, this was the solution to FB, of course. 4.7 amps is I times the length we said was 2 divided by the cosine of 55 times B, 1.8 Tesla, and we need the sine, we need the angle between I and B. Well, if we come over here, I is this direction here, B is this direction here, and this is the angle of 55 degrees. So when we come over here, the angle between I and B is 55 degrees. So for the magnitude, you can see 4.7 times 2 over cosine 55 times 1.8 times the sine of 55. But notice that sine of 55 is the same as, divided by cosine 55 is the same as tangent of 55. So we get the same magnitude here. Now let's consider the direction. This time we have minus j hat, that's the component perpendicular to the magnetic field, the downward component, cross I hat gives us a positive k hat. Okay, last one is BA. Well, here in the case of BA, FB is equal to 0. Why? Because you can see that I is in the negative I hat direction, B is in the positive I hat, and negative I hat cross I hat gives us 0. So we don't even need to worry about the calculation of the magnitude. But if you wanted to, when you come over here to put the angle, so you'd have, let's go ahead and write 4.7 amps times, this time it would be 2 meters times 1.8 Tesla. But the sine here would be the sine of 180, which gives us 0 anyway. So we don't even need to bother to go any further with that. Next question. Here we're shown a wire which is bent in the form of a semicircle of radius r, forming a closed circuit carrying the current I. The wire lies in the xy plane in a uniform magnetic field. It says find the magnetic force for segments 1 and 2 and then add them up. Well, the first thing I want to remind you is case 2 of our theorem. Case 2 said that when you had a loop carrying current, the magnetic force was 0. And folks, that's exactly what we're going to find. We'll go ahead and work them through individually and add them up, but case 2 says it all. If this is a closed loop, there is no magnetic force on it. Well, let's begin by looking at this region right here where we go from this point to this point along this wire. Well, case 1 of our theorem says when you have a bent wire, it's as though you have a wire of length L prime carrying current in the direction, and here this is from A to B here, so our current is in this direction, and the magnitude of L prime is 2 times the radius. Well, let's see, the magnetic field is upward, which is the positive j hat direction. The current is to the left, which is the minus I hat direction. So in this case here, FB, magnitude of I times L, which is 2R, times B. And here we weren't given the value of B. But let's go ahead and put minus I hat cross j hat gives us minus k hat. Now let's look at this straight segment here where we now have current in the positive I hat direction. So here we have this situation where I is in the positive I hat direction. B is still upward, which is the positive j hat. And so FB is equal to magnitude I times 2R times B. But this time, I hat cross j hat is positive k hat. So, just as we expected, the net result is 0. There is no net magnetic force in this loop. But if we would have recalled case 2, it already told us that when the loop is closed, there is no magnetic force on the loop. Well, this concludes the first part of the problem-solving session for Chapter 29. Until next time.